Hey everybody, welcome to our second part of our Chapter 7 notes. This is Module 7.2 over isosceles and equilateral triangles. For today's lesson, you'll need the following items listed on your screen. You might want to pause the video so you can go grab those. So as we're starting on page 327, you can see that we have a lot of vocabulary words here to learn. Our first section is on isosceles triangles. An isosceles triangle, as the text says, is a triangle with at least two congruent sides, so it's worth noting that there could be more than three. Those congruent sides are called the legs, and the angle formed by them is called the vertex angle. So over here on the example, here's a leg, here's a leg. We know that they are legs because they're marked congruent. Your vertex angle is as marked up here. And the one side that is different from the other two is called the base. On the ends of that base, you have two base angles. Those are here and here. The next little item in the book is for constructions, but we're going to save our constructions and do those later. So turn your page. And we have the isosceles triangle theorem at the bottom of the page. The isosceles triangle theorem says, if two sides of a triangle are congruent, then the two angles opposite those sides are congruent. Underneath the box, you'll see that it's also called the base angles theorem and can be stated as well as base angles of an isosceles triangle are congruent. So let's draw ourselves a little diagram to kind of make some more sense of that. We're going to start with a triangle. Draw it as close to actually isosceles as you can. Try not to make it look equilateral or like a right triangle. And we're going to mark the two legs congruent. So for me, these two sides, here and here, are going to be the legs. So across from each leg is an angle that kind of goes along with that. We'll talk more about that in 7.3. So across from this leg is the only angle in the triangle that does not touch that leg. And this angle corresponds with this side. Likewise, across from the other leg, you have another base angle, this one. And you'll notice that I've marked these with matching marks for matching measures. That is what the base angles theorem and the isosceles triangle theorem is indicating, is that across from the two congruent legs, you have two congruent angles as well. If you turn the page one more time, we have the equilateral triangle theorem. And the equilateral triangle is also an equiangular triangle. If equilateral talks about the triangle having three congruent sides, equiangular means that it has three congruent angles. And both will happen in the same triangle. The equilateral triangle theorem, as it says in the box, says that if a triangle is equilateral, then it is equiangular. So here's our example. We're not going to do the proof with that. We're just going to use it to talk about the different parts that are corresponding. So if angle A is formed by these two sides, the side all the way opposite from that has this relation. That's a terrible description. Pause. Uh-oh. My cursor's stuck. There it is. Slide across the page to page 331, and let's look at some examples of properties of isosceles and equilateral triangles. We're going to put some numbers with it, and hopefully this will help us make a little more sense out of these properties. It says Katie is stitching the center inlay onto a banner that she created to represent her new tutorial service. It is an equilateral triangle with the following dimensions in centimeters. What is the length of each side of the triangle? So what we always need to do is to make sure that the information from the text gets drawn onto the diagram. And as you can tell in this triangle, not all of the information is down here. If you're just looking at the markings, it looks like this is an isosceles triangle, but our reading says that it's also equilateral. So equilateral means that all three sides are going to be the same. And so once you have that extra piece of information, it's really easy to see that you're going to take 4x plus 7 and 6x minus 5 and set those two equal to each other. Just like that. From there, you're just using your basic algebra tools to solve this equation. We're going to subtract 4x from either side. We're also going to add 5 to each side. And then lastly, we're going to divide by 2. And we get that x equals 6. But before you get too excited, make sure you go back and check to see if you're actually solving for x or if you're solving for something else. And in this case, we're solving for the length of each side. So we need to take this 6 and we need to plug it in. Because all 3 sides are the same length, it really doesn't matter which equation you use to plug in 6. So I'm just going to use the one on the bottom. 4 times 6 plus 7. 6 times 4 is 24. Plus 7 is going to give us a total of 31 centimeters for each side. Next, we have triangle RST, and we're trying to find the measure of angle T. We don't have any reading here, so we just have to go on the marks. And according to this triangle's markings, it is an isosceles triangle. And so an isosceles triangle has 2 base angles that are congruent, and we're going to use that fact to fill in angle S with some expressions that we can use. So if side TS is across from angle R, then angle R is going to be the same as angle S, because angle S is across from this congruent side, right? TS is congruent with TR, so angle R is congruent with angle S. So now we have all 3 of our angles filled in, and we can use our triangle sum theorem to write an equation. 3x plus x plus another x, all 3 angles, add up to 180 degrees, because there's 180 degrees in any triangle, as you'll remember from the last lesson. So we combine like terms on the left. We get 5x equals 180. Divide by 5, and x is equal to 36. Once again, we're not finding x. We're asked to find the measure of angle T. So we need to take 36 and plug it back into angle T. So if the measure of angle T is equal to 3x and x is 36, 3 times 36 gives us a total measure of 108 degrees. Let's do just 2 more examples. On the next page, page 332, number 5, it says find the measure of angle P. Angle P is right here. We don't have any reading to do, so let's look at our marks. We have 2 congruent sides, which means that this is an isosceles triangle. And once we have those congruent sides, we need to mark which base angles are also congruent. Well, if this is your vertex angle, it's the one between the 2 legs, then the other 2 angles are your base angles. So angle P is a base angle and angle Q is a base angle. And base angles on an isosceles triangle are congruent. Just like we did in our last example, if we know that angle P is the same as angle Q, we can put a value in angle P so that it's not blank anymore. So angle P is now going to be equal to 3x plus 3, because that's what is over here with Q. And again, these 2 are congruent base angles. Now we can use our triangle sum theorem once again. We're going to add up angle Q plus angle P, 3x plus 3, plus angle R, and all of that equals 180 degrees, because every triangle has 180 degrees inside. We're going to combine like terms. 3 and 3 is 6. 6 and 5 is 11 x's. Also going to combine our integers. 3 and 3 is 6, minus 2 is 4. Then we subtract 4 from both sides, and 11x equals 176. Divide by 11, and x is 16. But once again, we need to check and make sure that we're solving for the right thing. We're supposed to be solving for angle P, so we need to take this 16 and plug it in. So the measure of angle P is equal to 3 times that 16 we just found, plus 3. So 3 times 16 is 48. 48 plus 3 is 51 degrees for the measure of angle P. For our last example, number 6, it says Katie's tutorial service is going so well that she is having shirts made with the equilateral triangle emblem. She has given the t-shirt company these dimensions. What is the length of each side of the triangle in centimeters? Again, it has an equilateral triangle, and we don't have anything marked on our sides. We do have these angles that are already marked, and from the angles or from this word equilateral, we could figure out that all 3 sides of this triangle should be congruent to each other. So if the 2 sides are congruent, we're going to set their measures equal to each other. So 3/10 y plus 9 is going to be equal to 4/5 y minus 1. Because I see that I'm going to be combining these fractions, I'm going to go ahead and turn 4/5 into an equivalent fraction that has a denominator of 10. So I'm going to multiply both the top and the bottom by 2, so that instead of 4/5, I'm going to work with 8/10. After I've done that, I'm going to go ahead and subtract 3/10 from each side. 8/10 minus 3/10 is going to give us 5/10 y. I'm also going to add 1 to each side. So 9 plus 1 gives me 10. We can reduce 5/10 into 1/2. And then to get rid of 1/2 y and have just a single y and have our problem solved, we're going to multiply times 2, because 1/2 times 2 is going to give us the 1 y that we need. 2 times 10 on the other side lets us know that y equals 20. Once again, double check to make sure that you know what you're solving for. The question asks for the length of each side, not for y this time. So we're going to take that 20 and we plug it into either one of these equations because they should be the same length. So I'm going to do 3/10 times 20 plus 9. I'm going to simplify over here. 3 times 2 is 6. 6 plus 9 is 15 centimeters on each side of the triangle.